इनका वो कहोगे चैट। Hello students, welcome to today's lecture. In today's lecture, we are going to learn about systems of particles and rotational motion. NCERT section 6.8, 6.8.1, and example 6.7. This is disclaimer. Learning objective. By the end of this lecture, you will able to understand the concept of translational equilibrium, rotational equilibrium, couple, principle of moments, and mechanical advantage. All right. So in today's lecture, we will cover first 6.8 equilibrium of a rigid body. Example 6.7, 6.8.1 principle of moments. Now our topic is equilibrium of a rigid body. So the word equilibrium. So a rigid body or a equilibrium. So basically a rigid body is said to be in equilibrium when it is at rest or moving with constant velocity. No linear acceleration. This is the first condition. Second condition, it is not rotating or rotating with constant angular velocity. No angular acceleration. It means a rigid body is said to be in equilibrium when no linear acceleration and no angular acceleration. So, if we talk about the definition, so we can say a rigid body is said to be in equilibrium when net external force as well as torque acting on the body about center of mass or any other point is zero. So from the definition, it is clear that net external force as well as torque acting on the body is zero. It means there is a no linear acceleration, no angular acceleration. So when both conditions are satisfied, so when we can say the body is in equilibrium. All right. Example. Suppose we have a book and resting on the table. So this book we can say in equilibrium when there is a no linear acceleration or no or we can say no angular acceleration. So when there is a no linear acceleration, no angular acceleration, the book is in equilibrium condition. So we can say the net force on the book is zero and there is a no rotation. So the book is in equilibrium. So this is the condition of equilibrium, and this is important concept because in upcoming slides we will use equilibrium, we will use rigid body, we will use net force, we will use net torque. All right. So a body is said to be in equilibrium. There is a no linear acceleration, no angular acceleration. So there is a two types of equilibrium. First, translational equilibrium. Second, rotational equilibrium. So first we will discuss translational equilibrium. So translational equilibrium means when total force, that is vector sum of all external forces acting on the body is 0. So we can say the body is in translational equilibrium. The important point here is this: vector sum of all external forces acting on the body is 0. It means if we talk about the translational, so here we will use external forces. And if we talk about the rotational equilibrium, in that case we will use external torque. So here this is translational equilibrium. So vector sum of all external forces acting on the body is 0. So there is a no linear acceleration. No linear acceleration means body is at rest or moving with constant velocity. If body is moving constant velocity, it means there is a no linear acceleration. All right. So the net, or we can say the total force, that is vector sum. So it will be F1 plus F2 plus Fn. So this addition shows the vector sum of all external forces that is acting on the body is equal to 0. Listen carefully. Here we talk about the translational equilibrium. So the net vector sum of net force, or we can say net vector sum of all external forces on the body is 0. So in the form of summation, it will be I equal to 1 to n Fi equal to 0. So this expression, listen carefully, 6.30a, this shows there is a no linear acceleration because the net external force acting on the body is 0, or it is at rest or moving with constant velocity. So this is the all about the translational equilibrium. In a scalar form or component form, we write uh, summation I equal to 1 to n Fix equal to 0. Summation I equal to 1 to n Fiy equal to 0. And summation I equal to 1 to n Fiz equal to 0. So this is the scalar form of the force. So net force is equal to 0 in all, along all axes, x axis, y axis and z axis. All right. Where Fix, Fiy and Fiz are the forces on ith particle along x, y and z axis respectively. So if the total force on the body is 0, then the total linear momentum of the body does not change with time. Okay, so this is the conservation of linear momentum. Next, or we can say second type of equilibrium is rotational equilibrium. Rotational equilibrium, we can say when total torque, that is vector sum of all external torque acting on the body about any point, is 0. So in that case, we can say the body is in rotational equilibrium. The word rotation. So if any body having rotational equilibrium, in that case the net or the angular acceleration of that body should be 0, or we can say body at rest or moving with constant angular velocity. Constant angular velocity means their angular acceleration should be 0. All right. So according to definition of rotational equilibrium, the net torque, or we can say total torque, that is the vector sum. So the total, suppose we have a n particles. So in that case, the total torque of that is acting on a system. So tau 1 plus tau 2 plus tau n is equal to 0. So this is the uh, external torque acting on the body about any point is 0. Here, this summation I equal to 1 to n tau I equal to 0 shows there is a no angular acceleration. There is a no angular acceleration. So in component form, we can write summation I equal to 1 to n tau I x equal to 0. Summation I equal to 1 to n tau I y is equal to 0. And summation I equal to 1 to n tau I z equal to 0. So here, tau I x, tau I y and tau I z are the torques on the ith particle along x, y, z axis. Yes or no? So there is a main difference between the translational equilibrium and rotational equilibrium. And what is that? So first, if we talk about the translational equilibrium, there is a we can say total their linear acceleration equal to 0 or net force, or their linear acceleration is 0 or body at rest or moving at a constant acceleration. And if we talk about the rotational equilibrium, their angular acceleration is equal to 0. We can say body is at rest or moving with constant angular velocity. All right, the difference is clear in both translational equilibrium and rotational equilibrium. And in simple words, we can say that in translational equilibrium, net force, that is a vector sum of all external forces acting on the body about any point. Or in rotational equilibrium, net, or we can say total torque, is the vector sum of all external torque about acting on the body about any point is 0. Both force and torque are vector quantity. It has both magnitude and direction. That's why here we use the word that is vector sum, not a simple algebra. Vector sum, because both quantities are vector quantity. All right. So if the total torque on the rigid body is 0, so the total angular momentum of the body does not change with time, because the net torque or total torque on the rigid body. Equilibrium of rigid body. So we can say a rigid body is said to be in equilibrium, both translational and rotational equilibrium, if both its linear and angular momentum are not changing with time. So it means if we talk about the translational equilibrium, so there is a no angular acceleration, or their angular velocity is constant. If they are linear, there is a no linear acceleration in case of translational equilibrium. And if we talk about the rotational equilibrium, so there is a no angular acceleration. Their angular velocity is 0. So if we combine both, if both linear and angular momentum are not changing, not changing, because the condition is in translational equilibrium, linear acceleration 0, and in rotational equilibrium, angular acceleration. So that's why the angular momentum are not changing with time. This is the condition. Or the second, in the second terms, or we can in simple terms, we can say the net external forces and net torque on the body should be 0. All right. This means the body has neither linear acceleration and nor angular acceleration, or we can say body has a linear constant velocity and constant angular. Yes or no? So if a rigid body is in translational equilibrium, then rotational equilibrium condition is independent of location of the origin about which the torques are taken. It means if we say said uh, if we say the body is in translational equilibrium, So in that case, rotational equilibrium is independent of the location of the origin. So if net force on the body is zero, net force means uh, vector sum of all forces F1 plus F2 plus Fn is equal to 0. The net torque about any point being 0 implies that net torque about any other point is also 0. Examples of translational and rotational equilibrium. So first, uh, consider two parallel forces. So we have a, a small rod. Their mass is very negligible. The mass of the rod is negligible. So we have a small rod and two parallel forces are acting on the rod. So at the two ends A and B, two ends at end A and end B, two forces are acting here. Both are equal in magnitude and acting along in same direction. So at point A, the force acting vertically here towards down. Similarly, and at point B, the force acting downward. So both forces are downward. So let's see. This C is the midpoint of AB. So if C is the midpoint, so what happened? Tell me. So if the C is the midpoint of the AB, so we can say CA equal to CB. The distance between AC and BC are equal. Alright. So that is equal to A. So the moment of force is at A and B will both be equal in magnitude. That is AF. Yes or no? From C to A, if we talk about CA. So AF, if we talk about CB, it will also AF, but in opposite. So net torque on the rod is 0. So the system will be in rotational equilibrium, but it will not be in translational equilibrium, as net force on it is non-zero. So here in this line, the important concept is this. So suppose the system will be in rotational equilibrium. Rotational equilibrium, what is the meaning? Meaning is there is a no linear acceleration. No linear acceleration means body cannot rotate. If body cannot rotate, so we can say this is in rotational, but it will be not be in translational equilibrium. Not be in translational means what? So it will be, it translate it translate from, it changes the position because the forces are acting at the ends of the rod, so it changes the position with time. So the net force on the on it is non-zero. Yes or no? This is the important. The body, the system will be in rotational equilibrium. It means there is a translational equilibrium. There is a no translation, or we can say body, it is not be in translational equilibrium. Yes or no? So if the not body is not be in translational equilibrium, so we can say there is a some forces. There is a some forces that is acting on the body, but there is a no linear rotation. If there is a no linear rotation, the body will be in rotation. All right. So example of translational and rotational. So now consider two forces again. So these forces are equal in magnitude but act in opposite direction. Uh, Magnitude of forces are equal. It means uh, we can say, suppose two forces F1 and F2 that is acting at the ends of the rod. So F1 or F2 in terms of magnitudes are equal. but their directions are opposite and perpendicular to the road as shown in the figure 6.20b. All right. So F1 and F2 both are opposite, both are having in opposite direction. So next what? So road is in translational equilibrium, but not in rotational equilibrium. Yes or no? Yes. Body is in translational equilibrium because there is a no linear acceleration. Body, but body not in rotational, not in rotational equilibrium because there is a force that is acting in that is acting at the ends of the rod. So the force due to the force that is acting at the end of the rods arises ro- uh, rotation here due to the force that is acting at the end. So due to this force, there is a angular acceleration. So there is angular acceleration, so body can rotate. So net torque is a non-zero. All right. So net torque is non-zero, and net force is zero or not? Yes, net force is zero because there is a no linear acceleration. Yes or no? Yes. Couple. So if we talk about the couple, so it means we can say when two forces, listen here, when two forces of equal magnitude are acting in opposite directions with different line of action, known as couple. So here line of action is an imaginary line along the direction of the force and passing through the point where the force is applied to an object. So suppose we have a rod and we applied some force at the ends of the rod. So the direction of the force are different, or we can say opposite direction. So we can say their line of action is also different. Also different. Yes or no? So example, when we open the lid of a uh, bottle by turning it, our fingers are applying a couple to the lid. So this is the best example of the lid. So we can say when you twist a bottle lid, your fingers apply a couple to it. A couple is a pair of equal and opposite forces that are not in same line of action. This condition of the forces creates a torque, which is what causes the lid to rotate and open. Yes or no? Second is Earth's magnetic field exert equal and opposite forces on the poles of a compass or needle. These two forces form a couple. So when a compass needle is placed in the Earth's magnetic field, the magnetic field exerts equal and opposite forces on the north and the south poles of the needle. These forces being equal in magnitude and opposite in direction and create a couple, which causes the needle to rotate and align itself with the Earth's magnetic field. So these two are the best example of couple. Forces of equal magnitude acting in opposite direction with different line of action. All right. Example 6.7. So that moment of a couple does not depend on the point about which you take the moment. So think about it. You have some time. Let's solve this question. So here couple is a system of two forces that are equal in magnitude, opposite in direction, and not acting along the same line. It means the line of actions are different. So here we consider a couple as shown in figure 6.22 acting on a rigid body. So at 2 points, A point and B. The force is F and minus F act respectively at points B and A. These points have position vectors R1 and R2 with respect to origin O. So the force is F and minus F respectively at points B and A. So these points have position vectors R2 and R1 with respect to origin O. Clear? So let us take the moments of the forces about the origin. So the moment of the couple that is equal to sum of the moments of the two forces making the couple. So sum of the moments, the two forces making the couple. First, mathematically, let's see. So first R1 cross minus F due to minus F force. Second R2 cross F. This is clear due to capital F. Now solving this equation, you will be get tau equal to R2 cross F minus R1 cross F. So R2 minus R1 cross F, because here F is the common. So, but R1 plus AB, listen carefully, R1 plus AB is equal to R2. Hence, AB is equal to R2 minus R1. Yes or no? This is the displacement. The moment of the couple, therefore, is tau equal to AB into F. So, from this illustration, it is clear that it is independent of the origin about which we took the moments of the forces. So, from tau equal to AB into F. So, this is independent of the origin. So, from this expression, it is clear. Yes or no? Okay. Principle of moment. So, let's see. For a rigid body in rotational equilibrium, where the net torque is 0, sum of clockwise moments or torques about any point must be equal to the sum of anti-clockwise moments or torques about that. So, let's understand it by a best example. So, the example is a seesaw. So, imagine a seesaw. If two people of different weights sit on opposite sides, the seesaw will only balance if the moments, or we can say turning effects caused by their weights, are equal. The heavier person will need to sit closer to the pivot to the balance the lighter person who is the sitting further away. Here pivot means the center of the seesaw. This one. This is the center of the seesaw. So this is the principle of moment. So we can say principle of moments, also known as what? Tell me. So principle of moments states that for a rigid body in equilibrium, the sum of clockwise moments about any point is equal to the sum of anti-clockwise moments about the same point. Moment means a moment is the turning effect of a force and calculated by multiplying the force by the perpendicular distance from the line of action of the force to the pivot point, the point about which the turning effect is considered. Alright. Principle of moments applied to a lever. So consider a light rod. The mass is like here we neglect pivoted at point O. This is fulcrum. So F1 called load is applied at a distance D1 load R, and F2 called effort is applied at distance D2 from the fulcrum, from the O. So D1 and D2 are the distance. So for translational equilibrium, there is a no linear acceleration. So net force on the rod must be 0. So it will be what? R minus F1 minus F2 equal to 0. Yes or no? Here F1 and F2 both are downwards. So F1 plus F2, we can say R minus F1 plus F2. So when we open the bracket, so the expression is R minus F1 minus F2 equal to 0. So the rotational equilibrium, sum of moments about the fulcrum must be 0. So it will be D1 F1 minus D2 F2 minus 0 into R equal to 0. Here we choose the uh, light, or we can say light rod. So D1 F1 minus D2 F2 equal to 0. So we can say D1 F1 is equal to D2 F2. So load of arm into load. Here D1 is the load of arm and load, that is F1, and load of effort arm is D2 and effort is F2. Alright. So now mechanical advantage. So mechanical advantage is defined as the ratio of load to the effort. Mathematically, when forces F1, that is load, and F2, that is effort, are applied at distances D1 load arm and D2 effort arm from the fulcrum, or we can say from O. So mechanical advantage, it is F1 divided by F2 is equal to D2 divided by D1. Okay. So here D2 is greater than D1. The mechanical advantage is greater than 1, means that a smaller effort F2 can be used to lift a large load. Now summary. Equilibrium definition. A rigid body is in equilibrium when both net external force and torque about any point are 0. Translational equilibrium. Vector sum of all external forces must be 0. So summation I equal to 1 to n Fi equal to 0. This is the only valid for translational equilibrium. And rotational equilibrium, vector sum of all external torques about any point must be 0. So mathematically it will be summation I equal to 1 to n tau I equal to 0. Alright. Couple two equal and opposite forces with different lines of action, where moment of couple is independent of point of rotation. So it will be tau equal to AB cross F. Principle of moment. Sum of clockwise moments equals sum of anti-clockwise moments about any point. So D1 F1 is equal to D2 F2. This relation is very important. So remember this. D1 F1 is equal to D2 F2. Alright. So mechanical advantage, ratio of load to effort, giving mechanical advantage of a lever. ma is equal to f1 divided by f2 is equal to d2 divided by d. Now we have some questions, practice questions for you. So please note down. This is a homework. First, a rigid body has zero net force but non-zero net torque. Is it in complete equilibrium? Why or why? Clear? I think this is a very simple question. Second, two equal and opposite forces of 10 Newton act on a rod with their lines of action separated by 2 meter. Calculate the magnitude of the couple. So here you have to find out the magnitude of the. Third, in a seesaw, if a 60 kg person sits 2 meter from the pivot, where should a 40 kg person sit to the balance the seesaw? Fourth, in a lever, if the effort arm is 5 times the load arm, what is the mechanical advantage of the system? Alright. Fifth, if a rigid body is in rotational equilibrium about point A, will it necessarily be in rotational equilibrium about any other point B? X. So this is the practice questions for you. Alright. Thank you for your attention.